In mathematics, we sometimes run into situations that seem absurd, like trying to raise -1 to the power of pi. And we sort of think to ourselves, how in the world can we make any kind of sense out of that? Well, very often it's the case that if we're willing to move into the realm of complex numbers, imaginary numbers, that things become more clear. And that's going to be the case with what we're going to talk about in this video, which is trying to figure out what -1 to the power of pi actually is. Now, we're going to begin by looking at this function. F of x equals -1 to the power of x. That's an innocent enough looking function. The formula doesn't seem to be too complicated, but actually this is quite a difficult function to try to understand in any kind of deep way. And if you don't believe me, try to graph the function. And good luck trying to graph it. Now, of course, there aren't any issues if we just plug in a whole number, an integer for x. So if we plug in an even number for x, we get 1 as an output. If we plug in an odd number, we get -1. But notice what happens when we plug in 1/2. Well, f of 1/2 is -1 to the 1/2 power, which is the same thing as the square root of -1, which is I. So notice already we have an imaginary number here when we let x be 1/2. Now, what is f of pi? That's ultimately what we're trying to find. We have -1 to the pi power. Now, this one is particularly challenging because not only do we have the negative base here, but we have an irrational exponent. So pi is an irrational number, meaning that it cannot be written as a ratio of integers. Now, an irrational exponent in and of itself is not too hard to deal with. So for example, if we have 5 to the power of pi, what does 5 to the power of pi mean? Well, 5 to the power of pi, what we do is we take the decimal expansion of pi, so 3.141592 and so on, and we raise 5 to these farther and farther out decimals of pi. So 5 to the 3, 5 to the 3.1, 5 to the 3.14, and so on. And we continue that on. Now, 5 cubed is pretty simple. That's just 125. What does 5 to the 3.1 mean? Well, 3.1 is really 31 over 10. So this just means the 10th root of 5 raised to the 31st power. Then we get this decimal for it. And then 5 to the 3.14, it means 5 to the 314 over 100. So we take the 100th root of 5, raise it to the 314th power, and we get this decimal. And we continue on in this fashion. These numbers, these outputs, the decimals are going to get closer and closer to a certain number, 156.9925 and so on. And this is what we call 5 to the pi. That's really how we define 5 to the pi, is the limit of this sequence. Now, why doesn't this same process work for -1 to the pi? Well, if we try the same thing for -1 to the pi, first of all, we can begin with -1 cubed, and that's no problem. That's just -1. But what about -1 to the 3.1 power? Well, 3.1 again is 31 over 10. So this is the same thing as the 10th root of -1 raised to the 31st power. Well, the fact that we're taking an even root of a negative number means that we're going to have to use imaginary numbers. But as soon as we're using imaginary numbers, something kind of strange happens. If you take the 10th root of a number, you're going to get 10 different answers. So -1 has 10 different 10th roots. And then we take each of those 10th roots and raise them to the 31st power. We would get 10 possible answers here. And it would get even worse if we did -1 to the 3.14, because we'd have the 100th root of -1 raised to the 314th power, but there are 100 different 100th roots of -1. So defining -1 to the pi in this same way is going to run into all kinds of problems. So how do we define -1 to the pi? Well, we're going to write -1 to the pi as e to the natural log of -1 to the pi. Now here, natural log is really the complex natural log function. It's usually written as just log. But the complex logarithm is really just the inverse of the complex exponential function. And you can do many of the same things, has many of the same properties that the ordinary natural log function has. So for example, we can bring this pi out front. So we can rewrite this as e to the pi times natural log of -1. Now, you might think, well, we're stuck at this point because you can't take a logarithm of a negative number, right? We all know that. In fact, probably our high school teacher told us you can't take a logarithm of a negative number. Well, your high school teacher was wrong. Sort of wrong, anyway. You can't take a logarithm of a negative number if you're only willing to stay within the real numbers. But we can talk about complex logarithm, complex natural logarithm of -1. So let's think about logarithms for a second here. What is log base 2 of 8? Well, log base 2 of 8 is 3, right? Because 2 to the third power equals 8. That's what it means to say log base 2 of 8 is 3. It's 2 to the third power equals 8. Well, if we were trying to find natural log of -1, what does that equal to? Well, natural log, the base, of course, is e. The question is really e to the what power equals -1? And you might think, well, there's no possible answer. E to anything is always positive. And in fact, think of the graph of e to the x. Doesn't the graph of e to the x always lie above the x-axis, right? E to the x is a positive function. So how could e to something be negative? Well, it turns out that e to the pi I is -1. In fact, this is a very famous result that is a consequence of Euler's formula. Now, Euler's formula says e to the I theta equals cosine theta plus I sine of theta. And I'm going to make a video on Euler's formula at some point. And when I do, I'll put the link to that video in the description of this video. But notice, for example, that if we let theta be pi, we get e to the I pi, or e to the pi I, equals cosine of pi plus I sine of pi. But cosine of pi is -1, and sine of pi is 0. So e to the pi I is -1. Now, it's also true if we add or subtract a multiple of 2 pi to theta. So, for example, e to the 3 pi I, we would also get -1. Or e to the 5 pi I, we would get -1 as well, and so on. So notice when we're trying to figure out what is natural log of -1, the question was really e to the what power equals -1. Well, notice it's e to these odd multiples of pi I. So we can kind of think of this as pi plus 2 pi k times I, for where k is an integer. So notice that when k is 0, we just get pi I. When k is 1, we get 3 pi I. When k is 2, we get 5 pi I. And of course, we can also let k be a negative integer as well. And then you might think, well, how can natural log of -1 be multiple different things, right, depending on this value of k? Well, it's kind of similar to when we talk about what is the square root of 25. Well, we say it's 5, of course, but aren't there really two numbers that if you square them, you get 25? So not only is it true that 5 squared is 25, but it's also true that -5 squared is 25. So isn't it kind of like there are two square roots of 25? We just by convention say that the square root of 25 is 5, but there's really two different possible numbers that if you square them, you get 25. So same thing with natural log of -1. There are multiple different values of natural log of -1. In fact, not just two of them, infinitely many of them. And this is really a property of the complex logarithm function, that it is multi-valued. Okay, so if we write this out, we get e to the pi times natural log of -1. The natural log of -1 we found was pi plus 2 pi k times I. And if we distribute the pi, we're going to get e to the pi squared plus 2 pi squared k times I. And notice this is of the form e to the I theta, where this is our theta. So we can write this as equals cosine of that theta, cosine of pi squared plus 2 pi squared k, plus I sine of pi squared plus 2 pi squared times k. So that again comes from Euler's formula. E to the I theta equals cosine theta plus I sine of theta. And I've written this out a little bit better here. -1 to the pi is this right here, but notice this is a different value for each value of k. So for example, when k is 0, we get cosine of pi squared plus I sine of pi squared. When k is 1, we get cosine of 3 pi squared plus I sine of 3 pi squared. We can let k be any integer, including negative integers. So notice -1 to the pi is really a set of numbers. And by the way, each of these numbers is on the unit circle. In fact, I've graphed this on Desmos. Now, I've graphed the unit circle here, x squared plus y squared equals 1. And make sure you're in complex mode if you try to do this on your own here. This is complex mode in Desmos. And I've plotted these points. Now, when k is 0, we get our first point. So it's really cosine of pi squared plus I sine of pi squared. That's this point here. When k is 1, we get another point. K is 2, we get another point, k equals 3. When we get up to k equals 7, it almost looks like the points start repeating themselves, but these 2 points are separate. They're not on top of each other. And as you continue on further and further and further, you're going to fill in more and more of the unit circle. The points will never repeat themselves. And you're going to end up getting a set of points which is dense on the unit circle. Now, when I say dense on the unit circle, I don't mean that every point on the unit circle is taken up. What I mean is that no matter how small of a little arc you pick on the unit circle, you'll always be able to find at least one of these points that's within that little arc. In fact, really infinitely many points within that little arc. So -1 to the k is really a set of points on the unit circle that's dense on the unit circle. So I've typed that out here just to be clear about it. -1 to the pi is a set of complex numbers, a set which is dense on the unit circle. So finally, we can look at this function a little bit more closely, -1 to the x. Well, of course, if we have -1 to an even power, so like -1 to the fourth power, our answer is going to be 1. But this would actually be the same answer that you would get if you rewrote -1 to the fourth as e to the natural log of -1 to the fourth, just like we did with -1 to the pi. It turns out in that case, you would just get this one answer of 1. And of course, if we had -1 to an odd power, so like -1 to the fifth power, we would get -1 as a result. Now, if we take -1 to a rational power, so let's say -1 to the 16/5 power, it turns out in this case, what we would get in this particular example is 5 different values of -1 to the 16/5 power. So if we rewrote this as e to the natural log of -1 to the 16/5 power and did the same thing we did with -1 to the pi, we would see we get 5 possible outputs. In fact, if we go in here to Desmos and do the same thing we did before, but this time with -1 to the 16/5 power, well, when k equals 0, we're going to get a point here. When k equals 1, we get another point. K equals 2, 3, 4. But when we get to k equals 5, it looks like we don't get a new point because what happens is we get this same point over again. And then k equals 6 is going to give us this, k equals 7, and so on. And we're going to get these same 5 points that are going to keep cycling around. And these 5 points, it turns out, form a regular pentagon. So whenever you have -1 to a rational exponent, if you reduce that rational number into lowest terms, then the denominator tells you how many possible values there are for -1 to that rational number. So -1 to the 16/5, we have 5 different possible values for -1 to the 16/5. And if we have -1 to an irrational number, so -1 to the pi or -1 to the square root of 2 or -1 to the e, then we're going to again get a set of points which is dense on the unit circle, really infinitely many different values for -1 to an irrational number.